All right, welcome to the workshop part of our session here at WorksWith. First, a note, we have 2 breakout rooms available, and these are manned by at least a Scilab's FAE and one of our user success engineers. So if you have any questions about installing Simplicity Studio, working with your Thunderbird Sense 2, or general questions about Edge Impulse, head to one of those rooms and we'll be able to assist you straight from there. But let's go build, a model to actually do proper monitoring of things in the physical world using the Scilab Thunderbird Sense 2. So what do we need? Well, the little dev board, naturally. Take it out, beautiful. Love the form factor on this thing. Really love that it also has a battery holder, BLE radio, and actually a microphone with really good gain, plus a bunch of other sensors that we can utilize here. So that's one, that's the hardware part. We also need Simplicity Studio 5. That, if you don't have that installed right now, I would suggest to do that, to get that process started basically now, because it might take a while to actually download all the dependencies. And we'll need that because we're going to build a custom application using a machine learning model that we're going to create in the next hour and a half. All right, so that's the hardware part and the software side. Then also we need something to detect. So I was looking around a little bit in my house. This is not a virtual background, it's actually my living room. For stuff that we can easily detect, I have gone with something I can actually do behind my desk. But if you have a better idea, please go ahead. But the same kind of principles that we use with real customers with industrial use cases in detecting stuff, for example, steam flowing through a pipe, actually applies here. So even if you do it with just water, this will translate very well to industrial use cases. And easy demo. Is water flowing, yes or no, from my Doppler into a glass and the other way around? Straightforward demo. So what is kind of the problem that we're trying to analyze here? Well, we want to record data. We can look at, let's say, a second worth of data. And then we have a binary classification problem. There's water flowing or there's no water flowing. That's it. As I like to say, everything starts with data. So the very first thing that we need to do here is start capturing data, both of water being poured into the glass or back into the Doppler, and situations where there's none of that, and just background noise, me talking, for example, or other things that you hear in the setting where you want to deploy this. So starting with data. So we can actually do the data capture using the Thunderbird Sense 2. To do that, we have built a custom firmware, and that firmware has binding code to kind of all the sensors on the dev board, plus it has a protocol, serial protocol, that allows us to capture that data straight from the device. So this gives you access to the raw data as we receive it from the device, so nothing downsampled or at lower resolution. In addition, we do some stuff like cryptographic signing of this data, so you know which device generated that. Not as important as we're just doing here a workshop, but becomes much more important once you deploy this at scale. So go to edgeimpulse.com and then head to the docs page. And then here on the left, you'll have the Silicon Labs Thunderbird Sense 2 board with a nice little schematic. So this kind of contains everything you need to get started. The one thing that we're interested in here is the latest Edge Impulse firmware. And once you download that just gives you a bin file. So to flash that onto the Thunderbird Sense 2, USB cable, dev board. So the Thunderbird Sense 2 has an onboard DAP link. So that's a secondary MCU that just iterates itself as a USB mass storage device. I think this is really, really cool. Before starting Edge Impulse, I worked at ARM for a very long time, and DAP-Link was one of the things that came out of the software business that ARM was developing. I think it's absolutely brilliant because it lets you program this device without having to install any driver or without having to use an external J-Link. So we have the TB004 USB flash drive. You see it here on my screen. This might look like a real USB drive, but any files you drop here will just flash the main MCU on the target, and then it will disappear. So it's kind of a fake USB drive. So what I do is I take the .bin file that I had and I just drag it here. This will take 20 seconds or something. You'll see it copying here. And once that's done, our device is basically ready to do the data capture. And you can see that actually the right firmware is running because it will play a little, I don't know, well, you saw that. Let me reset. It will play this pattern. There we go. Nice little rainbow effect. So cool, this is running. Now onto the interesting part. So we need an Edge Impulse account. We can go back to edgeimpulse.com. If you don't have it, just click sign up, follow those steps. It's really quick. You don't even need to verify your email address. I'll go here and actually log in with a demo account. And I want to create a new project. So we'll call it Scilabs Industrial 2021. And that brings us to our empty projects. So the first thing we want to select is what do we actually want to do? And based on that, we'll load a bunch of presets that will help you assist building this model. So here we actually want to do something with audio data. So we want to listen to what is happening around us. And yeah, stuff you can build with it. You'll see it listed here are voice interfaces, listening to keywords, or audible events. And hear what's kind of happening here. That's something we want to do. We'll select. There's a whole bunch of information on like connecting your dev board. If you already have audio, you can just use the uploader to get that, to upload that. And we have tutorials both for voice-related things and for recognizing sounds, a bit similar to what we're going to be doing now. So let's get started. If you are using Google Chrome, we have a very nifty feature, and that is that we can capture data directly from this dev board from the browser. Nothing else required. So as you've seen so far, we don't need any drivers to flash the Thunderbolt Sense 2. And we can even do the data capture without having to have external tools. I would suggest if you do more with this to install the Edge Impulse CLI, and that is available. If you go to the Thunderbolt Sense 2 page, you'll see the installation instruction here, the Edge Impulse CLI. It's very easy. Just install Node.js and then run this install script, and that will give you the Edge Impulse daemon. The daemon locally gives you a couple of things. So first of all, it can just keep running in the background, whereas for the integration with Chrome, you need to have that page open and reconnect every time that you refresh. That is one. The second thing is that we can do faster data capture. So in Chrome, we're limited to the serial interface at 115 kilobit, whereas here we can do it much faster. We can switch baud rates. In addition, there's a whole bunch of other tools available in the CLI, like a serial monitor, which we'll need a bit later, an upload tool, etc. So stuff that it does here is, well, we'll run the daemon. It will detect the device sitting here. It will ask me, actually do clean. It will ask me which project I want to connect to. So here, the Scilabs Industrial 2021. And there we go, done. So that's connected over the daemon. Alternatively, you can do it directly in Chrome, so let's quit that. let's go to Chrome. We select here, connect using web USB. We can select the J-Link OB. So there's a J-Link on there, sorry, not a DAP link. Click connect. And that's it, also done. So very straightforward. So either of these things is fine. If you just want to capture some quick data, use the Chrome one. If you're going to do more with this, get the CLI one. And the instructions should be pretty clear, so just head to the Thunderbird Sense 2 page. Follow that in the meantime. It should be installed in a couple of seconds. If you have any questions, go to one of the breakout rooms and we'll be able to help you there. So that's it. So we have a completely empty project, no data collected yet. But let's change that. So my label here, let's do it pouring. Let's position my Thunderbird Sense 2 here on actually close to the glass of water. And I hope that this is going to be picked up by my microphone. So I select the microphone I have in front of me. So select the sensor, the built-in microphone. I select the sample length, so how long do I actually want to capture the data. So let's set 5 seconds. The data frequency here fixed at 16 kilohertz because the microphone on the Thunderbird Sense 2. And let's just do this. Let's click start sampling and I'll start pouring water. So actually to clear some flash, that's why it took a little bit longer to start doing that. The good thing is it doesn't really matter. I started pouring that water already before we started pouring that water already before the device is actually listening, but we can cut that. So let's see how well it works. Okay, I am going to take a bigger container because this is going to be really hard to get this data back in. Wait, I'll be back. All right, I have 2 bottles now, and let's try that again. All right, let's see how well that was being picked up by the microphone. Okay, I'm not sure how well you guys can hear this, but there is definitely some water flowing. Here I start a little bit later, so I actually can go to crop sample and then look at kind of the place where I hear something. So it's about this mark, I think. Then this actually updates, so you can just say play. Okay, so that definitely is something. Cool. All right, that is one. Let's actually try that a little bit longer. Maybe let's do 10 seconds. I'll pour it back. And then we just crop whenever we need. So you can actually look at the lights on the device because they will turn orange whenever the data is actually being recorded. So that is a quick way of actually finding out what is happening there. take a look. Because they will turn. Okay, so here definitely pouring. Let's crop this again to get my voice out. Okay, that is pretty good. You might think, well, this sounds a little bit quiet, but that's fine. Kind of the ML model will be able to pick this stuff up quite well. So let's try that again. Actually, we're going to try it 2 more times. So we at least have a little bit of data. Then we collect some noise data while we're at it. And we're just going to train the very first version of this model and see how well it actually does stuff. So we have an idea of whether this model is going to work, yes or no, pretty quickly without having to kind of dive into building the full model out. So I'm going to do that again. Now I'm going to go from 1 to the Doppler. Okay, I actually think this is easier to detect. So going from the glass water bottle into the Doppler, but whatever works kind of on your end, that is up to you. My suggestion is while we're kind of doing this and reading that data back from the device, I'm going to do all of this model building in real time. My suggestion would be do the same thing. If you haven't set up your device yet in the first 15 minutes of this worksheet so far, go do that now. And then find some stuff that you can detect in-house and build this model the same time with me, so that in 5 minutes or something we'll actually have decent enough data. Let's actually see. Okay, so here, very clear. Let's cut off the first 2 seconds. There we go. That was pretty beautiful. All right, let's try that again. Amazing fun job that we have. Grew up as a software developer and now we're just pouring water into stuff. I'm gonna be quiet here a little bit for the next 5 minutes or something, so you guys can do something here without interference from me when talking. And I'm gonna collect a few more of these samples until I have in total 1 minute of data of water being poured. All right, so I have about 1:07. I'm going to delete the very first one. It's too short. And it was the other way around. So now we actually have a data set, except for the first one, where we kind of pour data from the glass bottle into the Doppler unification. So that's one class. Now we also need kind of the I'm not pouring water. So the nothing or noise kind of class that we have often. So one way is naturally to say, well, I want to add noise. And I can kind of do the stuff that I would normally do around here. So I talk a little bit. I can be quiet for a while. Yep, move the bottle around. So that is one way of actually building up the data set. We do have, because this is kind of the type of data that you often reuse, we have pre-built some of this data. So you can go to our pre-built data sets in the docs, keyword spotting, and there you have a noise folder after you download that. And that had all kinds of like background and static noise. So that is a really quick way of getting some of the data in. So yeah, you see here all kinds of like air conditioner stuff, airport things. So let's actually get, and there's I think 15 minutes of data here, but that is, you want to have some data balance. So you want to have almost as much noise as much pouring sounds here. So we want to add maybe 50 seconds of data here. So let's go to upload existing data. We can choose our files here. And we'll just select some. So we definitely don't need this full data set, but it's kind of nice to have a bit of separation of everything. So there's not a single kind of dominant noise class where we only say, well, we've only collected data of people at the train station, which is one of the samples we have in here. But rather that we have kind of a nice little mixed data set. This is running water. That's something we don't want to have in our data set. Go to so that's 74 files, so 74 seconds. Now I'm going to show you a little trick. So far we've just been collecting data into our training data set, and that's the data that we're going to be using to train this model. You typically want to hold some data aside where you can use for validation of your data set. And that's data that goes into the test set. So when you upload data, we can automatically split that for you. So as said, we maybe only need 50 seconds or 55 seconds of training data. The rest we'll throw in the testing data set. So here, our label will be noise and upload. There we go. And now we have a nicely balanced data set here. About 1:11 of noise, 1:04 of pouring, and our test set has 13 seconds of noise. So let's actually add some data into our test set as well, where we're going to be pouring data. So we actually have this balanced data set. And that then kind of our initial data set will be complete. So let's connect back to the device. Once again, we record data, but now this data is going to the test set. All right. Now you might think, Jan, wait, in total now we've collected about 2.5 minutes of data with the training set and the test set combined. Isn't that little? Yes, definitely. So my suggestion would be here, If you want to build this model out, definitely add a lot more data. But we can get an idea of whether the data that we've collected actually is suitable for machine learning already with a relatively small data set. And we have a couple of nice tricks to up the amount of data. So training tool is done. All right, excellent. This looks good. So we have our data set here. So with our data set, we're going to train an impulse. And an impulse is kind of the name that we give for a complete data pipeline that consists typically of, well, first of all, I want to split my data up into something. So here we're looking at time series data. All of our noise samples are a second long. I think that is a nice window that we want to look at. The longer the window, the more compute you need, naturally. So it's kind of a careful balance. And that means that for our pouring data, we'll cut that up into seconds in 1 second windows. And to artificially up the amount of data that we have, we can set our window increase. So let's say I have a 2 second pouring sample. I could say, well, I'm creating 2 samples per second from that, from 0 to 1 second and from 1 second to 2 seconds. Or we can say, well, we actually create more data because we take 0 to 1 second, then 0.5 to 1.5 seconds, and then 1 second to 2 seconds. So you up that data a little bit. As said, class balance is important. So we have almost as much pouring data as we have noise data. So in this case, let's actually set it to 800 milliseconds. So a little bit of overlap, but not much. Let's zero pad the data just in case. If one of the noise samples is shorter than a second, we want to pad that with 0 at the end. And then we add a processing block. It's kind of weird maybe saying this as a CTO of a machine learning company, but I like signal processing a lot better than I like machine learning because signal processing is explainable. I understand what it's doing and it's reproducible as well, right? It's very deterministic. I throw a waveform into a DSP algorithm, I get the same results out at every point. So we try to do as much as we can already with signal processing. So cleaning up the data, removing noise, all that kind of stuff. And then from there, we'll actually develop this stuff further, and we train a machine learning algorithm to kind of do the final classification between these things. But the DSP already has done a lot of work for us in cleaning up this data and highlighting the interesting frequencies, for example. So for audio, we have a whole bunch of different blocks already. So for human speech, for example, we have an MFC block. For other data, we have MFE blocks, so using mil filter bank energy into a spectrogram, or we can use a raw spectrogram. And I think actually on this data, I've not tried it, but I think a normal spectrogram will actually do pretty well already, so no normalization. If you say, hey, this is interesting, I want to add my own custom DSP block, or I already have some data in DSP, just remember, edge impulse is not just for audio data or just for accelerometer data. You can kind of model any type of sensor-based analysis into it. Just click the add a custom block link and you get a tutorial there. Here, let's add a spectrogram. And then we want to add a learning block, and we want to classify what is happening. So is it pouring or is it noise? So we'll add a classification block. That's it, save impulse. And what we're going to get out of it is 2 features. So I'd like to think of this after it's done as developing a driver. So rather than I ask my temperature sensor, what is the temperature? I ask my model, like, what is happening? And that it then incorporates raw data from the microphone is one thing, but what I just get out is 2 features. The prediction of how much of this signal you think is noise and how much of you think is pouring. So, all right, let's go to spectrogram. One thing I forgot. Let's actually go back to dashboard and select under latency calculations, select the Thunderbird Sense 2. Why is that important? It's because modeling something that will actually work on device is really key, right? I can create an amazing model, but if it then doesn't work on the Thunderbird Sense 2 because latency requirements or because it uses more RAM than is available, then that model is kind of useless. So at every step of the way, we're going to show you the performance numbers, and we can localize that for the Thunderbird Sense 2. So here we go. These on-device performance metrics are now customized for the dev board that we're working with. So, okay, so this is the DSP screen. So what we see here on top is the sample that we're currently looking at. Here we have some parameters. Here the frame length and the frame stride control the number of columns here on the time vector. And then the number of frequency bands controls like how the granularity of the signal here. And it goes from 0 to 8,000 hertz because our data is at 16 kilohertz. If I set the frequency band to 64, you know, you'll see less granularity here. This process is pretty fast, so this is for a second worth of data on the Thunderbird Sense 2. It takes about a quarter of the time, it's not bad. We can play a little bit with this by upping the length and stride, and it goes up to goes down to 115 milliseconds. So maybe that is actually better. Let's do something like that. Cool. Under 78 milliseconds, 20K of RAM. That fits nicely on the Cortex M4F. But let's actually take a look and see the difference between noise data and our pouring data. So pouring is pretty sparse, and that is probably something we don't want. Like, it's pretty heavy, and it could be because the noise floor is set here at 52 decibel. So let's actually remove that altogether. And we see quite a bit like here in the low spectrum, and we see kind of these little peaks. I think that is when the water kind of hits the other thing. It might be fine to do it like that, but I think maybe if you set it to 72, this becomes a bit more clear. Although there's kind of this this information in the high frequencies that we might not be interested in. Here it's pretty clear. So let's actually maybe set it to 62. If you think, hey, this is a little bit tedious, Jan, like why do I need to do this as a developer? There's something for that. It's called the Eon Tuner, and that helps you kind of find these parameters by hand or automatically. So you don't need to do it by hand. But I would like to kind of show what goes into the designing of that. Like, don't treat the Eon Tuner as a magic button that will find the optimal model for you. Think of Edge Impulse as an engineering tool, like your IDE. So kind of designing this in the same way is, I think, really helpful. The cool thing here is that what we see here is a lot of energy kind of centered in the very low bands of what is happening. And that is something that we see on pouring in kind of all the samples that we have. This one might be a bit problematic. We might need to remove it at the end. This is the very first one where I threw data into the glass bottle. Let's actually remove that right now. So we have a uniform data set. So all the data that we now have in this data set is always data going from the glass bottle into the Doppler. So consistent stuff. So now let's set that back. And minus 62. Cool. And then that kind of signal you don't really see in the noise data, right? Like, this is someone typing, so that's naturally much different. Here, there is a lot of noise in the data, but there's a lot more energy in the signal a bit higher up as well. So let's see. So on first sight, this looks pretty decent, but let's actually generate features from this data. And from that, we can do something interesting, and that's the feature explorer. So after the signal processing step, we can create a visualization that will kind of show you how well your dataset separates. And that gives you, it's a very good indication of dataset quality very early on. So that is here. And that separates actually really nicely. So we see a nice cluster of noise here that is unlike any of the other stuff in the dataset. Then we have a nice cluster of orange here. A little bit of like blue stuff on the side. So that apparently it looks a little bit like. And then we have some data here, another cluster. Okay, so here actually there's a little position at this point where I was not pouring anything, and then it starts again. And it actually clustered that differently. So this is actually a problem with my data point here. So I could go back into the sample, actually crop it or split it into two separate samples and remove that part. But I think it's kind of interesting to see the separation here. So this looks actually pretty decent. We do have very little data, but that's kind of the part of doing this in real time in a session. So let's go train a model. So yeah, let's actually set this to 30 and let's see if the model actually converges a little bit. So what we have here is a neural network architecture. So our input is a spectrogram. And then we have, how I like to think about this, I think I said it in the presentation as well, is machine learning is you give the computer the input, so here the spectrogram, and you give it, oh, this should be pouring, this should be noise, and it tries to find this mathematical formula. The number of parameters in that formula and kind of the sort of formula that you have, that is the neural network architecture. So we try to pre-populate that with something that we think is going to work for the type of data that you have. But if you have a data scientist that knows the stuff really well, they can click on the little icon here, say switch to expert mode, and they can build something from there. If you want to have different presets, you can go here. So 2D convolutional is a bit more compute intensive, but might perform better. However, we have so little data and it separates decent right now that I don't know if it's going to be necessary. And the Eon tuner again can find this stuff for you automatically. So you train a model, it converges quite quickly. So we see kind of the accuracy on the test set or the validation set. So that's, we split the data up earlier in the training set and the test set. In the training set, we keep 20% of the data aside again, and that's what we use for validation. So we do pretty well here, 96% accuracy. It is actually really good at pouring. Sometimes actually when the label is noise, it predicts pouring. So that is something you probably want to optimize for. I'm not going to spend much more time on that at the moment, but we can highlight kind of the stuff that goes wrong. So here actually it thinks it's pouring. Yeah, that's actually me talking. I have no idea why that's the case. This is the hard part. This is why I like signal processing better than machine learning. But in general, actually looks decent. And yeah, the one here with a complete silence in it, in the pouring, gets classified as noise, which is kind of what we would expect. So this model does seem to be very decent on that. So a kind of good next step is kind of go to model testing and see how well it performs there, because this is data that the model has never seen, can't optimize for at all. And now I actually see that I mislabeled it. Okay, so this actually, this is good. So the data that we collected in the test set, I poured data in, but I actually labeled it noise, and now we see that actually it thinks it's pouring all the time. So it's a data error on my end. Let's actually rename that to pouring and edit the expected outcome to pouring as well. And classify again. But you see that on the noise stuff, everything is right. And here on the pouring stuff, everything is right as well. And once again, you can kind of dive into the different clusters and see like what is happening here. But I am actually surprised a little bit. Like it's doing its job really, really well, at least on the data set we collected. Let's try that out on the dev board itself. So we can go to live classification and use the daemon or the web USB again to get the data in. And then classify it. So let's get my data back into the class container. And let's actually do a state transition here as well. So we'll first pour some water and then we'll actually do nothing, and then let's see what it does there. All right. So what we do here is we still capture just the data on the device, so nothing is running on device yet. But it gives us a good indication, and it's a really, really quick feedback loop because you don't need to install anything on the device. You just capture some more data, classify it, and this is the way to kind of verify whether the model is going to run nicely, yes or no, straight from there. Let's see. All right, so classifying. And cool, so actually see that state transition happening. So for the first 3 seconds or so, we're pouring data. Then there's kind of this in-between place where we don't really know what we're doing, and then we go to noise. So that is cool. We can also see kind of where this data is in our data set. So you see the pouring data is in this pouring cluster, and then the moment that we start doing something else, it jumps to this cluster of data here. So it's cool. We built a model. And hopefully you did too while you're watching this. Let's deploy it on device and see if it works there too. So you can go to deployment, and the quickest way of validating your model really on device is by selecting the dev board. So here the Thunderbird Sense 2. Click build. Then we take your complete model, we compile it to source code as I explained in the presentation, and then we build in the cloud. We build a binary for you. So that is the same binary as we downloaded at the very beginning of this workshop from this page, but with your model loaded. So you can still do the data capture and all of that. You don't need to refresh that firmware, but we embed your model into that, and that way you can kind of very quickly evaluate if there's something weird going on or whatever. So that's it. So we're spinning up a Simplicity Studio environment here in the background and building that and loading Eclipse. So it takes a little bit. This is a really great way of evaluating. And then if this works nicely, we are going to export this data as a library ourselves into a custom Simplicity Studio project. And we'll actually write some code to do other things like blink LEDs or whenever we hear pouring water, or and we can even stream some data over BLE. I'll show that as well. But let's first wait until this is done. I'm gonna pour some Diet Coke into my mouth. Okay, there we go. So we have the new bin file. Once again, same as we did before. Drag the bin file onto the TB004. Now to see the results, there are 2 ways. You can use a default serial monitor connected to the board at baud rate 115200. And you can control the device from there with AT commands. Just type AT plus help to see that. Or if you have the CLI installed, we have the edge impulse run impulse command, and that kind of does all the stuff for you. So there's 2 ways of running this command. So in normal mode, we listen for a second, print the classification. So that's kind of the easiest way. There's also continuous mode. And there we constantly run. So we use a DMA interrupt to get data from a microphone, calculate part of the spectrogram, and that way we can do 3 or 4 inferences a second on this hardware. So we're going to do both. Let's first try. All right, so noise, 0.7. I think that's something we saw earlier. We can train a little bit longer to kind of get the noise a little bit higher, but that initial stuff works. You see the data here, sorry. So, and yeah, the DSP takes 120 milliseconds, really quick, classification 23 milliseconds. So that's 1 second of audio analyzed on an M4F running at 40 megahertz. So this is really quick. you have a lot of kind of other stuff available to do stuff in your control loop. Let's try it with pouring too, and then I'll just leave it running for a bit. That is excellent. Okay, so as said, the second thing that we can do here is continuous mode, and that runs 3 or 4 times a second. So this is really great for stuff where you can't miss anything. Here we do listen for a second, stop, listen for a second, stop, which is kind of fine for like stuff like pouring, etc. But in continuous mode, we can constantly listen, and we implement that on the device. So you run it with Jimples run impulse continuous. Okay, and that's kind of what we want, I think, in our application, because now this is just much faster, right? It responds immediately. Hopefully you heard that when it does stuff. So, okay, we have a model. It works. Really awesome. You might think, why is DSP less here? It's because we only calculate 1/3 of the DSP. So we do this 3 times a second. So that's a bit faster. But the classification we still run in the full window. All right, so we have prepared a project for Simplicity Studio, and you can find that by going back to the Scilab Thunderbird Sense 2 page and then clicking this link, Jimples firmware for this development, blah, blah, blah. Click that, and that brings you to this page. The moment that I'm recording this, we're 2 weeks actually prior to Works With. These instructions are still for Simplicity Studio 4, but by the time that you are watching this video, Simplicity Studio 5 instructions are here. Go through that right now and import this project in Simplicity Studio 5. If you have any issues, please go to one of the breakout rooms where people will help you. It should be really easy. You can download the source code here through the code download zip, and importing that data is then in the README file, and it should be straightforward, especially if you've ever built anything in the past in Simplicity Studio 5. I will give you 2 minutes to figure that out. I've done that already, so I have the project open here. I try to see if I could make this larger, but I can't actually in Eclipse. I can make the text larger, but that's basically it. And in 2 minutes, I'll come back, and I'm going to show you how you import the import your model into this project. Okay, I hope people have imported this into Simplicity Studio 5. If not, head to one of the breakout rooms. Will help you there. So, in our project, in our Jimples project, on the deployment page, we'll now click the C++ library, and that will give you, well, that the kind of name says it, a C++ library. So this comes with no external dependencies, and it can be compiled with any modern C++ compiler, so that's really awesome. Let's build it, and that will give us a zip file. So this comes with our SDK, and your model and kind of everything that is needed here. So stuff you see in here is our SDK. You see your model parameters, so which DSP blocks went to that, like the spectrogram block, and your neural network, or if you use some other model, like a regression model or anomaly detection, it will be in here as well. Okay, so these three folders together make up your model. So let's go to Simplicity Studio, delete. You should delete the SDK folder as well. I'm not going to do it because of time, otherwise I need to recompile all of that. But delete the Edge Impulse SDK folder, the model parameters folder, and the T of Light model folder here from the Edge Impulse folder. So delete. Yep. And then we drag these back in, and then it will ask us to copy files and folders. That's something we want to do. That's it. Updated the model. So now when we build this project, we will get kind of our model. So now what you get out is exactly the same firmware as we built earlier straight from Edge Impulse. Naturally, that is, okay, cool, great, not that interesting. Let's actually make it do something interesting. For example, light up an LED whenever we hear pouring of water. So we have some code here to turn the LEDs on and off. I'm going to copy that. So our control loop here in this firmware is in just an SDK platform, Silicon Labs EI main maybe? No, it's run impulse, but where is that? Where is that? It would be so useful to... So this is probably possible in Eclipse or in Simplicity Studio. I just don't know how to find a file. Oh yeah, EI run impulse. Okay, so this is the code there. We control the device, so we have... Oh, this actually works really nicely. So we have selected the microphone because we're collecting data from microphone. This is actually embedded inside the model that you just imported. So if you look at model metadata, it has stuff like, oh, Jongboom demo made this project. It's called the Scilabs Industrial 2021. It has 16,000 frames input. And the sensor that we're using here is the microphone. Very nice. So let's... and so yeah, this is kind of the loop that we run whenever we inference, and we want to use the continuous one. So run and continuous. So this is the function that we're going to run when we run this inference loop. So yeah, let's see. So it's very simple. We call the run classifier continuous function, then we get a structure back, the result structure, and that just has a classification object. If I can click on it. And that just has a label and a value. That's it. So you can write code in the same way as you would write a normal control loop to do stuff here. So I can say, let's say, heard pouring. And yeah, we can see here if result, let's here compare result classification ix.label and pour, Jesus, equals 0. So if this matches and the value is above 0.8, then heard pouring is true. This is incredibly slow. This is a 16-core machine with 64 gigs of RAM, and still I get Eclipse on its knees. So herd pouring is true, and then here we can say herd pouring. We can actually turn the LEDs. Let's try that in here. I think I need this one as well. All right, so if you're herd pouring, I want to do LED. That doesn't actually happen. EI LED, let's say yellow. Otherwise, I'm going to turn it off. So this is kind of the most basic control loop that I could write here. Yeah, let's try it out. Project, build project. Let's hope I didn't make a mistake here. Oh, RGB set LED is not there. So that is in one of these functions, I think. No, it's an extern. Yeah. So. All right. Let's try. There's the perils of live demoing stuff here at a workshop. But this gives you a little bit of time to actually completely get your model up and running here. All right, build finished. Let's try this out. I think it might be faster if I just go back to my project and flash it that way. All right, so I have my GNU ARM v1020. You can flash this through Simplicity Studio as well, but this seems more reliable to me. So we flash my custom binary now here. So one little note, so we run our impulse, so we run the model whenever we run this edge impulse run impulse thing. So what it does underneath is that it opens a serial connection to the board and then runs at run impulse a command. You probably don't want that. I want it for the video because I want to explain some stuff here, but if you don't want it, you can go to eimain.cpp and there's the EI command line handle, but you can just say run and then continuous, and that will just loop indefinitely. So that's a way to get around that and don't load the AT command firmware, and thus save a bunch of RAM as well. This is flash now. Let's try it out. I'm gonna connect an external camera, actually my phone, if this works. Yeah. All right, let me find my phone and actually show to you. New movie recording. You on iPhone? There we go. It's not running. Did I do something? Actually sorry about that. The whole thing keeps. Awesome. That was really cool. So we have something that now responds to, audible events. Really, really interesting, actually. I think for everyone that's really cool. So really easy to integrate this into your own control loop just by adding a little bit of code, and we've set all of this up. Now, naturally, it's a very small model. There might be interference. I saw some a little bit when I was talking, sometimes when it actually triggers. So that is stuff where we, after initial validation, say, hey, let's actually add a bunch more code. One other thing that I would love to show you here is that we can stream this data over Bluetooth as well, because naturally Silicon Labs typical silicon from Silicon Labs is much more than just a dumb MCU on a dev board. It actually paired with low power wireless communication. So in this example project, we actually have some code to send the data over BLE as well. So that is actually here. So if so we have the send classifier output, and that just writes I don't know where the implementation is exactly. It just writes data over BLE to a get characteristic. That's it. So that is a really easy way. So if you have a phone, for example, where you want to know what is being poured, you can get the data from there as well. So I think the key part here is the model that you get out of Edge Impulse is nothing special. You integrate it in exactly the same way as you currently write your application or currently write your control loop. So you leverage it in that case. So leverage in the exact same way as you would currently leverage a driver or something. So the example project that we put together here, it uses the latest SDK, I think 3.2. It uses latest IDE, and everything that you would normally do in Simplicity Studio just works. There's no dependencies, nothing on RTOSes, like a little bit on DMA buffers and stuff to get this data in, but like at the very basic level, there's zero dependencies on nothing. Integrating this model is really, really easy. If you want to see it without all the drivers and stuff, so it's a relatively complicated project because of that, you can go to running your impulse locally in the docs, and then to the Thunderbird Sense 2. And this actually is the very, very basic stuff. So no drivers, no nothing. Literally the only thing is this is how you load the model in, compile it, and get predictions out. But yeah, the last thing that I want to show you here is sending this data over BLE as well. Okay, wicked. So let me open. Light blue on my phone. So here we go. I see the Edge Impulse device. That is my Thunderbird Sense 2. Cool. I can go to the 2A56 UART principle. I click the UTF-8 thing. This works with kind of every BLE app that supports reading characteristics, which I guess is everything. And then listen for notifications. And let's run this. And now it doesn't go back to noise because the threshold is 0.7, and sometimes when I say something, it doesn't happen. Anyway, this logic once again, really easy to extend by, just really easy to extend just by going here. But really cool. It's out of the box. You can just stream this data straight over Bluetooth, which I think like the combination of this stuff is just really, 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 really powerful. So that concludes the workshop part. If you haven't finished yet, or you have some feedback, or you want to do something, head to one of the breakout rooms. We'll be happy to assist you a little bit after. If you see this later on demand, for example, and you have any questions, we have a fantastic community here at forum.edgeimpulse.com. Just see the insane amount of people asking questions. It's absolutely astonishing. So head there, ask your question. Both me and our user success people are always there to assist, and we can forward things to Silicon Labs if anything is needed there as well. The last kind of thing that I would like to stress, if you've managed to make it this far, I hope you have a pretty good idea of what we can do. One, we've been building something in real time. It's very, very small model. For just if you're still facing some stuff, like we see here, the noise doesn't go to, it only goes to 0.7, and there's still some false positives whenever I talk sometimes from the device. Add some more data. I just added here literally a minute, 30 seconds of data. It's absolutely astonishing that it even works. Add a little bit more data and iterate from there. Second, don't think of machine learning as a magic box. You throw some data in, you get a conclusion out. Use it as an engineering tool. We try to make it as clear as possible, kind of what the decisions are that you make and kind of how to influence device performance, which samples work well, which samples won't work well at every point, and use it that way as well. Actually look at the data here, like, okay, hey, here's a problem with my data set. Let's remove this from data or split this actually up. Iteratively build that up. Go sit with your team and collect more data in different sample and different environments, and really treat this as an engineering task. That is by far the quickest way to success. There's a whole bunch of really, really cool stuff that we've not gone into in this session. The most important one, I think, here is the Eon Tuner. So the Eon Tuner also supports the Thunderbolt Sense 2, and it's a perfect way of kind of finding the optimal values for your DSP parameters, your neural network parameters, within the constraints of your device. Because we can find the largest model that we can ever imagine, and that will, most likely maybe generate a model that really works. But if it's too large for the model or doesn't hit your latency or RAM constraints, requirements, it's useless. So the Eon Tuner will actually help that. Try that out. I think it's really cool. And yeah, the very, very last thing is, for me, doing stuff with machine learning kind of really brought back the spirit that I had back in 1998 when I learned to program in Visual Basic 6. The very first time you typed your name, Jan, and the machine said back, "Hello, Jan," in a message box. That was magical. And for me, and for I think a lot of the people in our community, machine learning has the same magical spark again. All of a sudden, your device, even if it's a little tiny dev board, as we have here, can all of a sudden understand the real world. And it can be anything where you say something or you do something with something that is happening, and it can actually know when that is happening just by listening or by feeling, or on the bit higher spec devices even like see the real world all around you. And that magical feeling is, I think, really cool. For me, it's really awesome, kind of the stuff that people build with this. Really brings a smile on my face. And I can't wait to see what you will build with this technology. And if you build something cool or build something interesting, if you have an amazing industrial use case, or if you do something amazing with conservation, just let us know, and we'd be happy to feature it, help you commercialize it even. So we are running a market development fund where people can apply for funding to bring this stuff to market. If you just want to have a chat with us to see like what whether the thing you want to build actually makes sense, just head to the forum, create a ticket there. Our users people are super enthusiastic, are experienced in building these types of solutions. So go ahead and try it. Just sitting behind a computer and seeing it does not do justice to how amazingly cool it is to have devices really respond to stuff in the real world. So with that, I want to thank you for watching, and I want to thank Silicon Labs for hosting. As said, we can't wait to see what you will build.